Related rates are a very uh, fun and popular type of problem in calculus. And in all related rates problems, what you're going to do is you're going to get, um, let's see, you're going to get some function is going to be related to some, some function f of, uh, let's just say, function f is going to be related to some constant g. So constant times g. So there's going to be two functions that are related. Um, and maybe g is squared or possibly it could be like cubed rooted or something like that. But there's going to be some relationship between a function, one function and another. So there's going to be some function f uh, and some function g, and there's going to be some relationship between the two of them. And then what you're going to want to do is we're going to be thinking about related rates. So what we want to do is we want to relate um, how one of these functions changes with the time and how it's changing with time with relation to the other. Now, this is a very general approach, introduction to related rates. But what I'm saying is that in every single one of these problems, they're going to give you two functions, f and g. And then you're going to have to find um, two derivatives with respect to t and relate them. And that's the whole crux of this topic, relating different rates. So let's think about it in terms of a very popular problem with an inflating balloon. And we're going to assume that a balloon is a perfect sphere. So it's a perfect sphere. And we know that the volume of a sphere is 4/3 pi r cubed. And that's the volume. And, and it says that it's being inflated at a rate of 10 pi cubic feet per second. So that is the change in volume. The inflation rate is how much our volume is changing, and it's 10 pi cubic feet, so feet cubed per second. At what rate is the radius increasing? When the radius is 2 feet. So as the balloon gets bigger and bigger and bigger, um, the different it's going to be increasing at a different rate. And what we want to know is how quickly is the radius growing at the moment when it's 2 feet. So what we need to do is we need to say, okay, well, I have this equation for volume that relates volume and radius. And in every single one of these problems, what we're going to do, since we want to relate their rates, we're going to take the derivative with respect to time of them. And they've done it right here, but just to do it again, we're taking the derivative with respect to time of my left side and the derivative with respect to time of my right side. The left side, we get dv dt. And the right side, we get 4/3 pi times 3r squared dr dt. And we want to find dr dt. We want to find that value when r equals 2. So, I just erased that other problem. We didn't need it there. So what we do now is we create an equation for dr dt. We know that dr dt equals dv dt divided by 4/3 pi r squared. Um, Now we can fill in what we know. So the change in rate of our radius with respect to time is dv dt. Well, that was given. That's 10 pi over 4/3 pi times the radius squared. Well, we're looking at we want to find dr dt when our radius is 4. So 2 squared. Well, simplifying this even more, we get, well, the pi's are going to cancel off, and we get 10 over 4/3 times 2 squared is 4, and this simplifies to 30 over 8, which equals 15 over 4. And what are the units? Well, feet per second, because we're talking about how the radius is changing, um, how the radius is changing over time. So really, like I said, you're going to start off with two functions. In this case, it was volume and our radius. And then we're going to take the derivative with respect to time of both of those. And then we're going to get some relationship between the two derivatives, dr dt and dv dt. And we had a relationship between v and r. And then we'll find some unknown. So let's do some more of these. Um, Here we've got a ladder that's 25 feet long, leaning against a wall. So there's a picture of it here. If it says that the foot of the ladder is being pulled away from the bottom of the wall. So we're pulling the bottom away at a rate of 14 feet per second. So if this is x, dx dt is 14 feet per second because we're moving that edge of the wall away at 14 feet per second. It says at what rate is the top of the ladder moving down the wall? So, in other words, the top of the ladder is going to be moving down, and we want to know what is this dy dt at the point when it's 7 feet above the ground. So we want to find dy dt at the point when y equals 7. Okay, so what we need to do is we need to get a relationship between x and y. So first thing, relate x and y. And the second thing, relate x prime and y prime with respect to time. So x and y, well, we've got a triangle. It's a right triangle. So we have x squared plus y squared equals 25 squared. So that's our first equation. And then our second equation, we need to take the derivative with respect to time of both sides. So we want to find d dt of x squared plus y squared, and that should equal d dt of 25 squared. So we're differentiating with respect to time because we're looking at speed. So we get 2x times dx dt plus 2y 2y times dy dt. So 2y times dy dt, and that equals the derivative of a constant, so equals 0. Solving for dy dt, because that's what we're looking for, dy dt equals, solving that out, we get negative x dx dt over y. Okay, so now I want to find dy dt when y equals 7. So I know that my y value is going to be 7, so I know this. Um, I know my dx dt is always 14, so I know this. Now I just need to find x. Well, I have a relationship between x and y, this relationship right here. I know that when y is 7, x, if I solve this equation, x equals 25 squared minus y squared square rooted. So x is going to be 625 minus 49. So this value, let's just leave it in square root. This is the square root of, let's see, 576. Yeah. Okay, so then dy dt, or the change in y with respect to time, equals negative x, where x equals square root of 576, times dx dt. Well, dx dt is 14 all over y, and our y value is 7. So this equals negative, simplifying this, negative 2 times the square root of 576, and it should be feet per second. And it makes sense that that value is negative because as I pull the ladder out from the wall, the height of the ladder on the wall should be going down. And what I'm doing now, just so that we can get a number on that, we have negative 2 times the square root of 576. So, oh, nice. I didn't know that was a perfect square. Huh. Equals negative 48. So, this equals negative 48 feet per second. So that's the speed at which the ladder is falling down the wall. When the height is 7, given that it's moving at a constant rate of 14 feet per second away from the wall. And that all came from getting two equations, the one that relates x and y, and the one that relates dy dt and dx dt. Let's do another example. Okay, so it says change of distance between two cars. So it says at a given moment, a car is 30 miles north of an intersection. So um, if we define this as north, east, south, west, so at some given moment, it's a car's 30 miles north. So this is 30 miles, and traveling toward an intersection at 45 miles per hour. So we say dy dt is negative 45. And why is it negative? It's negative 45 because we're moving um, toward the intersection, and so our distance is becoming less. So we've got a negative derivative. And at the same time, a truck is 40 miles east. So here's our truck that's 40 miles east, moving away. So its distance is increasing. So dx dt is 35 at 35 miles per hour. It says, is the distance between the vehicles increasing or decreasing at that moment? And at what rate is it increasing or decreasing? Well, this is an interesting question. The distance between the car and the truck is z. So what we need to do is we need to figure out what we're looking for is the distance between the vehicles, the rate at which that distance is changing. So is the distance between the vehicles increasing or decreasing? So what we're really looking for is dz dt. How do we find that? Well, let's find what we know. We know that z squared equals x squared plus y squared. Okay, that's always going to be true. It's a triangle. And then let's take the derivative with respect to time of both sides. So when we take the derivative of the left-hand side, we're going to get 2z times dz dt equals 2x dx dt plus 2y dy dt. Remember, what I'm looking for is how my distance z is changing. So that, if we solve for dz dt, we get that dz dt equals, well, all the 2's are going to go away. So just x dx dt plus y dy dt all over z. And I know everything except for z. You know, I've got my x dx dt, my y, my dy dt. I just need to find z. And so to find z, let's use this expression. I know that z squared is going to equal x squared plus y squared. This is a 3, 4, 5 triangle, so z is going to equal 50. So I get that dz dt equals my x value, 40, times dx dt, which is 35, plus my y value, which is 30, times dy dt, which is negative 45, all over z. And so if I do out the work, what I get, let's see, we can cross off a 0 from each of these. Zeros go away. We're essentially dividing everything by um, by 10. So 4 times 35, 0 is 140. 3 times negative 45, 135 all over 5. Oh, I love the way these work out. So this ends up being 5 over 5, which equals 1. So what does that mean? Well, it's a positive value. So because it's a positive value, the distance is increasing at a rate of 1, and what are the units? Mile per hour at that moment. Okay, so I'm gonna stop this, and we'll continue with some more problems in the next video.